Hello, and welcome back. In this video, I will be talking about differentiability. There's times where a derivative of a certain function does not exist. And if it does not exist, that means it's technically not differentiable. And also, I will be talking about notations. So, a derivative does not exist, mainly if the limit does not exist, that means the derivative does not exist. And I will go over that. First, I want to recap what I talked about in the intro to derivative video. The first is that the definition of derivatives, which is f prime at a equals limit as h approaches 0, f at a plus h minus f at a all over h. This is the definition. The second is that what it means. Basically, it means that it tells us the slope of a tangent of for the function f of x at a certain point, say x equals a in this case. And this also tells us the instantaneous rate of change of the function f of x at with respect to x equals a. And so, when are the cases when it's not what are the conditions for the derivative to exist? And that's technically just one, and that is the limit must exist. So limit must exist. That includes the fact that this cannot go into positive or negative infinity. And the limit and so if the limit must exist, then there are three conditions. This is also a recap. First one is that f at a, the point must exist. The second is the limit itself, the overall limit should exist. And the last one is that the point value must equal the limit value. Also, this will only exist if the left side equals the right side. So yeah, left side equals the right side. So when are the cases when it's not differentiable, when the limit does not exist? And there are kind of four cases where it's not. The first one is a cusp. And there are two reasons why the limit for this does not exist. The first one is, as you can see, that this is if you're going to say point A, if you're taking a derivative of point A, it's approaching infinity. So that's the first reason that it's approaching infinity at point A. The second reason is that the left side does not equal the right side. And this function, again, is also keep in mind that this function is differentiable, like say at this point, x, but it's not differentiable at a. The second is a corner, and a good example, like a corner will only occur if it's an absolute function, say. So the reason why the limit does not exist is because the left side does not equal the right side. Because if you're approaching from the left versus if you're approaching from the right, you're getting the opposite values. And yeah, that's the corner. And again, it's not differentiable just at point A. At any other point on the line, it is differentiable. The third is a vertical tangent, and you can see why it's not differentiable because the point it's if you take a tangent, it's approaching infinity. So this is the reason why it's not approachable, because infinity is not a defined value. The last one is it's discontinuity, and you can easily see why it's not differentiable because first of all, the left side limit does not equal the right side limit. The second, um, yeah, well, the second case will be if it's an asymptote where it's approaching an infinity. So this will be the second case why it does not exist, because it's approaching infinity. And once again, for both of these, it's just at point A. And at any other point on the graph, it is differentiable. So since we're done talking about differentiability, let's go with the last part, which is notations. There are three notations. The first one is M10 that you have seen. So you would put M10 equals limit as x approaches, say a, no, as h approaches 0, sorry. As h approaches 0 for f a plus h minus f at a all over h. And you can get this a certain value by saying m10 x equals a if you want to sub the value of x in. So this has to be x in that case. The second notation is that you might have seen, and it's kind of common, that is f prime at a. This is just used to if you're finding the derivative. That's all. Like that's the main case. If a function is given and you just need to find a derivative of that function at a certain point, you just use this value. Whereas if you want to find the tangent equation, you use this value, this notation. It's not really like forced on, but it's kind of preferred to use for the right purpose. The last one is it's a Leibniz notation. I'm pretty sure I pronounced it wrong. So this is the guy who came up with it. A small history lecture would be that, well, he lived from 1646 to 1716, and he introduced this um, notation. And in this his notation is dy over dx, and in this case, d stands for differential. This is preferred to be used in application basis. So if you want to find, say, the differential in distance over differential in time, or differential in velocity over differential in time, etc. But once again, like it's not like you will lose marks or anything, or you will, like, I don't know, be penalized for using this over that or this over that. It's just like preferred methods. And yeah, if you want to find at a specific point, you add an x equals a value. So that's pretty much it. And yeah, thank you for watching this video. It was a short video about differentiables. And please, um, to view more videos, go to our website aohl.info, and have a good day. Bye.